Today, what I'm going to talk about is insulated bond wire, passivated bond wire, and adhesively promoted bond wire by making use of aluminum oxide coating. This is the one-page summary of what I'm going to talk about today. Challenges for surfaces of bond wire. Challenges before encapsulation. Challenges after encapsulation. Before encapsulation, metal bond wire does not provide electrical insulation. Metal wires do not provide a corrosion passivation. After encapsulation, metal wire do not provide a good adhesion to epoxy molding compound. On the other hand, aluminum oxide coating can provide electrical insulation, corrosion passivation, and good adhesion to EMC. First, aluminum oxide coating on bond wire for adhesion promoter. On your left-hand side, wire cut is one of the typical failure mechanisms in harsh environment. Because of CT mismatch stresses, debonding occurs between wires and EMC. This is an interfacial fracture between the wires and EMC. This interfacial cracks grow long enough and then a wire cut occurs because the wire alone has to carry all of the thermal stresses without help of EMC. Typical solution is to increase the wire diameter because the bigger wire can carry a bigger stress. On your right hand side, if we introduce aluminum oxide coating on the surface of the conventional bond wire, you can increase the adhesion so we don't have interfacial cracking between a bond wire and an EMC, then so we don't get to have a wire cut failure. For instance, on the conventional bond wire without adhesion promoter, when we apply the position of a outer metal additional layer so that we can induce the interfacial cracking. And when we apply the stretch bonding, which is nothing but external mechanical loading, that's terribly very weak adhesion we have seen. However, when we introduced aluminum oxide coating as a adhesion promoter, we apply the stitch bonding, we don't get to see any interfacial cracking. From a different perspective, to cost reduction purposes, because now we have a better adhesion, then we can decrease the wire diameter for the cost reduction purposes. Electrically insulated bond wire. When a bond wire has electrical insulation, they may touch with each other. There's not going to be an electrical short problem. And for this particular application of a long wire between two semiconductor chips over the long distance, this bond wire has to withstand its own weight. This is not very easy to do, but when when a bond wire has electrical insulation, they may sag a little bit, they may sway a little bit, they may touch with each other a little bit. There's not going to be an electrical short problem. From a different perspective, if the wire is allowed to touch with each other, we can also reduce the diameter of a bond wire for the cost reduction purposes as well. On this slide, I'm going to explain how we ended up with coating aluminum oxide bond or aluminum oxide of bond wires. Previous work at the top ECTC last year, we presented aluminum oxide coating on PCB copper pad. This year, right now, we are presenting aluminum oxide coating on bond wires. On your left-hand side, at the top, you're seeing a gold wire bonded to a typical aluminum pad. This aluminum pad always has a native oxide on its surface, very thin aluminum oxide. However, it allows good bondability and reliability. That is described by this paper 2014. And on your right hand side at the top, we made the deposition of aluminum oxide on PCB copper pad in order to replace conventional surface finishes of gold and nickel on the top of copper. And we presented a lot of data in terms of bondability and reliability last year, ECTC. Today we are making a deposition of aluminum oxide on the surface of a bond wire. Why not? In the past, we have seen a good bondability with aluminum oxide. Aluminum oxide does not interfere with the first bonding and a second bonding in the same way as the aluminum coating on PCB copper pad before. You're seeing a gold wire bonded to the aluminum pad. We introduced aluminum coating on bond wire. There's no interference. And you're seeing a conventional bond wire bonded to the PCB copper pad. Here's the aluminum oxide coating. There's no interference. Looking at the second bonding, there's no interference as well. The only new risk coming in as we introduced aluminum oxide coating bond wire would be a free air ball formation and OCB because of the fact that a bond wire is completely surrounded by the aluminum coating. That's what I'm going to talk about in a next slide. Aluminum oxide was coated on a bond wire by making use of ALD, atomic layer deposition, because ALD is very well known for excellent conformal coating. Precursor for the ALD deposition is trimethyl aluminum, and H2O is a reactant. And as a result, you get to have aluminum oxide deposition. Byproduct is CH4. Single layer process, single process creates a 1/10 of 1 nanometer. So you're gonna have to repeat the same process as many as you want until you achieve desired thickness of aluminum oxide. On your right hand side, you're seeing a special chamber for coating aluminum oxide on a bond wire. This is the chamber for the ALD process. You're seeing a special spool for the wire or for coating aluminum oxide. When a wire winding is finished, this whole thing is moved into the chamber for the ALD deposition. On this slide, I'm going to show you the OCB sensitivity to the aluminum oxide thickness. The rule of thumb that we would like to propose is for the case of a gold wire, the diameter is greater than 1 meter. There's no OCB issue whatsoever. 6 nanometer thick, 8 nanometer thick aluminum oxide coating. However, when you look at an ultra thin bond wire, 0.7 mil, there is a very strong sensitivity to the aluminum oxide coating. When aluminum oxide thickness is greater than 10 nanometer, we're seeing a very serious OCB formation. As far as the gold wire is concerned, 5 nanometer thick, 6, 7 nanometer thick aluminum coating, OCB, there is no OCB whatsoever. We made a demonstration of a continuous bonding, 20,000 continuous bonding. We made use of a 0.7 mil gold wire and 6 nanometer thick aluminum oxide coating. After we've done many testings, we came up with a OCB ranking. Number 1, conventional gold wire. Number 2, gold wire with aluminum oxide coating. This is very interesting. Number 3, silver wire with aluminum oxide coating, but no forming gas. No forming gas is better for the silver wire than forming gas. On this slide, I'm gonna give you a little bit of sense of what the OCB mechanism is like. I'm gonna explain why OCB is affected by the oxide on the wire surface and oxide thickness. When electrical energy is supplied to the bond wire, the bond wire is going to melt, is going to have a molten ball, is going to grow, but the bond wire right next to the molten ball, I would call it a TBMZ, to be melt zone. It's nothing but a solid. Elevated temperature is very hot. When a metal is exposed to the high temperature, is going to experience metal oxidation. This oxide thickness depends upon wire material types and temperature. Of course, if this TBMZ oxide thickness is very small and thin, no problem with OCB. If this TBMZ oxide gets thick, it does not break down gradually during ball formation. Rather than that, for instance, here left hand side oxide layer is long, but it's not broken down yet. But on the other hand, on the right hand side, oxide layer broken down, this would create no symmetry situation, no axis symmetry situation. Material is symmetric, geometry is symmetric, and the molten ball is symmetric. But broken oxide layer on the surface of the bond wire is not symmetric, so it's going to interfere with the surface tension of the molten ball. That's going to trigger the OCB formation. This whole thing occurs over a very short period of time, so very difficult to provide like a proof of this phenomena. But anyway, so when thickness of oxide is very thin, the little interference with a molten ball surface tension, so there is a stability going on. On the other hand, however, when we apply aluminum coating on the surface of the bond wire in an artificial way, this is nothing but a passivation. So this passivation is not going to allow any additional metal oxidation of the bond wire itself, so that we can control the metal oxidation of the bond wire. As a result, you can control the OCB formation. At the bottom, you are seeing a typical mud crack of a very thin coating. Here, this particular paper describes the stresses in a coating layer as a function of a coating thickness. On this slide, you're seeing free air balls for the aluminum oxide thickness of like a 0.6 all the way up to 15 nanometer on a 1.1 mil diameter of aluminum, the gold wires, you can the like a bond wire was melted to form a free ball, and it solidified, and you can see the aggregation of aluminum oxide on the ball because wire was molten but aluminum oxide was not. The melting point of the aluminum oxide is greater than 2000 degrees C. But however, I want to emphasize this aggregation is not a dirt or contamination of any kind, because this aggregated aluminum oxide can make a good bonding with EMC resin and a ball bonding. So it does not make any degradation in terms of strength. Here I'm showing you bondability data for the 1.1 mil gold wire having an aluminum oxide thickness of 0, 6 nanometer thick, 8 nanometer thick. Fab size is same. Bonded ball size is same. Bonded ball height is the same. And we found the strength is same as well. Wire pull strength, ball shear strength, stitch pull strength. There's a little bit of a drop, but looking at a stitch fracture mode, they are all same. Here, the diameter is 0.7 mil gold wire and a silver wire, almost the same strength were obtained. Aluminum oxide coating does not change IMC types or IMC thickness between wires and pad metals. The resulting IMC surrounds the broken pieces of aluminum oxide. And aluminum oxide has a good adhesion to wire and pad metals. This is why bonding strength is the same for both no coating and coating cases of aluminum oxide. Reliability testing was done for the packages susceptible to wire cut failure mode during accelerated thermal cycles. Very, very serious temperature swing from -65 all the way up to 150 degrees C. The conventional wire started to fail at 1,400 cycles. However, aluminum oxide coated wires survived more than 2,000 thermal cycles. Please note that a diameter of the aluminum oxide coated gold wire was much smaller than a bare gold wire cases, 1.7, 1.2. Right now, apple to apple comparison testing is going on, 1.2, 1.2, 1.5 to 1.5. Diameters are the same for both no coating and coating cases of aluminum oxide. For the conclusions, aluminum oxide coating can provide adhesion promoter, insulation, and passivation to a conventional bond wires. Adhesion is increased by the introduction of aluminum oxide coating, and aluminum oxide coating enhanced OCB for the silver wire, and I show the same bondability, and the lifetime of the package improved during thermal cycles by making use of aluminum oxide coating. That indicates that we can decrease the diameter of the bond wire, and that a cost reduction is possible. Thank you very much for your attention.